Ladies and gentlemen, boys and girls, we don't see bugs like this very often. We are talking about one of the most beautiful exploits that I have seen in a very long time. Talking about copy.fail, a vulnerability that is a local privilege escalation that works on every distro of Linux since 2017. It is hands down one of the most beautiful exploits I've ever seen. We're gonna break it down in this video. I'm gonna talk to you about how it works, and I'm gonna run the exploit at the end of this video, so stick around for that. Now, I'm gonna be very clear. This is a complicated exploit. I'm gonna do my best to break it down as simply as possible while also leaving in the important details. I'm gonna try to strike a very delicate balance here, so if I fuck up on either end, I apologize, but it's just the nature of the game we're playing today, okay? Also, it took me roughly 2 hours to read the write-up, and I think fully understand the exploit, so I may make mistakes. Again, I'm trying my best. I apologize if I make mistakes. Copy.fail is a local privilege escalation. This is a vulnerability that requires you to have an access on a computer already, but if you're there on any version of Linux since 2017, you could use this vulnerability to escalate up to root. What's even more amazing about this bug is the fact that it is a logic bug, which means that it does not need to be patched for the certain kind of version of Linux that you're on, right? A lot of vulnerabilities like this have a certain race window or a certain kernel specific offset, something that changes between distros of Linux that you have to patch the exploit for, requiring a different version for every distro of Linux. In copy.fail's case, we'll go into the exploit here in a second, it is so pervasive that one 732 byte Python script allows it to run on every distro of Linux. Now, these cheeky fucks made their Python very hard to read, so I'm gonna have a beautified version of this here in a second. But this script on its own, just right here, will work on any version of Linux and will get you root on that box. The nature of the bug is actually very beautiful. There's a lot of really good detail in the write-up here. I'm gonna gloss over a ton of this because if I went into all the detail, it would take me probably 1 or 2 hours. But let's talk about exactly what's going on here. To understand this bug, we have to talk about this thing called a socket, right? In Linux, everything is a file, and a socket is a kind of file in Linux. Now, there are different kinds of sockets. We have the ones we know very well, like TCP and UDP, right? We can send data to external systems using the TCP and UDP stack. Also, we have the Unix socket stack, right? This is a way for programs inside of a system to talk to each other over messages that are sort of like TCP UDP, but it doesn't actually use the networking stack. Now, there are a variety of different socket types that all have their own underlying subsystem that allow them to do the thing they have to do. The one we're talking about today is the AF-ALG socket, okay? The AF-ALG socket is basically the socket subsystem that allows a user from user mode to do cryptographic algorithms using the systems the kernel has in place, right? This is a good thing. This is a thing that people should be using because what you should not do is roll your own crypto, okay? The way you do that is you use crypto algorithms that are already written for you in the kernel, and also this kernel may have access to hardware accelerators, right? Things that inside the CPU physically can do crypto faster than the CPU itself, which may allow you to get some more work done in a quicker time period. One thing about sockets that you need to understand is a socket is just another structure inside the kernel. Two important pieces of information about sockets are their input and output scatter lists, okay? A scatter list is a linked list of pages, offsets, and length, and then a next, right? So it goes to the next page. This is how the socket in the kernel knows where the user data lives for that socket. And the same thing applies to the output, right? So you have pages, offsets, and length. The reason for this, if I send over a socket 40,000 of the A, right? I send literally 40,000 A's, okay? Those 40,000 A's are gonna be scattered physically in the CPU across 10, I think, math hard, 10 or so different pages, all of potentially varying lengths inside those pages, right? So there has to be a way for the socket in the kernel to know where the data comes from, and so this is where the scatter list comes in. The scatter list tells the kernel exactly where the pages exist for the kernel to read from to do a socket operation. How do I transfer data from user land, the pages that I see, to kernel land, the pages the kernel sees? Now, the AF-ALG socket exposes a variety of algorithms for you as a user to do on that socket. Again, to use the hardware acceleration and the algorithms in the kernel to do the crypto. Now, one of them is the suite of algorithms that provide authenticated encryption with associated data. authentication and encryption are two different styles of crypto, but when you combine them, you get a very powerful dynamic where you can send data to a person and it be secure where no one can read it. But when it's authenticated, you also know who you're sending it to, or if you receive it, you know who you received it from. This is a great set of algorithms that allow you to do things securely in the world of cryptography. I know you're probably thinking, wait, is this a crypto lesson? Is this going to be a hacking video? When did we hack? It's coming, I promise. Okay, now the contract that the kernel subsystem for AEAD has is the expectation is you send the data in the following order. You have the authenticated associated data, you have the ciphertext, okay, which is the data that is encrypted, and then you have the tags. The tags is the data that is used to do the HMAC, which is the hashing media authentication code. This is like the signature, this is the authentication piece. And so when you send the data to the kernel via the socket, this kernel expects the data to come in this order. Now, before we talked about scatter lists, remember we have the input and the output. So when you send the message to the kernel via the send message, what happens is this set of pages are put into the input scatter list, okay? And then inside the kernel, what happens, it allocates new pages for the output scatter list, okay? Because again, we have to do some kind of crypto, and that crypto has to be done in a way that we can send it back to the user, which we can read out. When we do a read on a socket, it reads the memory out of the output scatter list. So it's going to copy all of this data into the AAD and ciphertext for the output scatter list, okay? But here's where it gets really hairy. And guys, before we finish talking about this exploit, stick around with me to talk about today's sponsor, Flare. Attackers are moving faster and faster every day. With the supply chain attacks we talked about, and this bug in particular, it's getting easier and easier for hackers to compromise an entire network. On average, it takes 48 minutes for once an attacker gets in to compromise an entire organization. But most organizations don't know that a credential has been compromised, some password floating around in the ether, for up to 36 hours. Flare can help you take that gap and shrink it from days to seconds. With Flare, all you have to do is put in the identities you're concerned about, like your email addresses or your domain names, and then Flare goes around the dark web and looks for hackers that are actively selling or exploiting the credentials that you know and love. And Flare just released their Entra ID integration, so if you use Azure, all you have to do is wire Flare up to Entra, and it will automatically ingest all the identities that are inside of your Azure deployment. And just like here, the Entra ID that I ingested got caught on the dark web, and Flare was able to send me an alert the minute they found out, reducing my time to response. Guys, you know the rule. The best way to help the channel out is to go interact with the sponsor. Go check out Flare now and see if it fits your organization's needs and stay ahead of attackers using exploits like this. And with that said, back to the exploit. Flare, thanks again for sponsoring the video. Let's go. The AAD data and the tags are on two separate pages, okay? Now this is the input scatter list, which means that it's only readable by the kernel. In theory, this is not a thing the kernel is allowed to write to. However, for the sake of optimization, the kernel uses a reference to the tags page as the output for the crypto algorithms. Matter here in a second. What we have now is two pages that contain data that we care about. This is the ciphertext and a reference to a tags page, okay? For one particular algorithm, an algorithm used in IPsec, so IPsec is a variety of, it's a suite of algorithms, but one of the fields inside of IPsec uses ESNs, or extended sequence numbers. They're a 64-bit, an 8-byte sequence of sequence numbers that track what order the IPsec data was sent in, okay? To compute the HMAC for the packet to do the signature validation, the algorithm temporarily writes signature data outside of this location. It writes it right here. It uses the old signature data as a temporary scratch pad. Which again, all of this is crypto data internally. Who really cares? What is bad about this? Well, this is where it gets crazy. Remember how I said previously that to populate the input scatter list, we do a send message, right? And the send message just creates a list of pages that contain the data. And we need to send the AAD, the ciphertext, and the tags. Well, what if instead of sending all of this data, what we did instead is we sent the AAD and the ciphertext, and then we called splice. Now, what splice allows you to do is take a pipe and pipe the data associated with a file descriptor and pipe it into a socket. What that allows you to do is take a page and append it to an input scatter list. Okay, a new page appears. Do the Super Smash Brothers thing. A wild new page appears. So what we're able to do, guys, I'm wrapping this up here. We do a send message on the first AAD and ciphertext of the data. Okay, then we do a open on user bin su. This opens the file descriptor, and as a result, we have page table entries in the cache of our process, okay? We then, instead of sending the tags, we are going to do a pipe, and we're going to use the pipe to splice together our crypto socket and the FD of our program to make it so that the pages that are open in the scatter list are our user data here, and then the page table entry for su, the local page cache entry, so that when the crypto algorithm runs, it writes 4 bytes of scratch data that we control into the cache page for the su program. Oh, and mind you, the splice function isn't just source and dest file descriptors. You also get to give it an offset. So we get to choose exactly how far into the user bin su binary in memory we want to write these 4 bytes. So we can write a 4 byte chunk at offset 0, a 4 byte chunk at offset 4, a 4 byte chunk at offset 8, etc., and use that to overwrite what the kernel thinks su looks like in memory, byte by byte by byte, or 4 byte by 4 byte by 4 byte, so that when we do an exec VE on user bin su, the kernel isn't going to go load it from disk, right? Because the loading from disk has already occurred. We already opened it. The kernel already has a cached page in memory. What it's going to do is open up and try to run the program su that we have, that we've overwritten with shellcode. Oh, and by the way, it still sees su as a set UID binary, so it's going to run the shellcode as root. So this is the POC. I had AI beautify it because the POC that was published previously is like really not easy to read. This is the POC with comments and proper variable names and stuff. So all the POC does is we set up the crypto algorithm to run using some key, some IV, and some other data. None of this really matters for the sake of the exploit. This is the gzip compressed shellcode, which again is just done for the sake of making the POC look smaller. It doesn't have to be gzip compressed. There's a function called write 4 bytes that allows us to write 4 bytes to a target FD at some offset and what 4 bytes we want to write. The way it works is, like I said, we create a socket that uses AFAlg, and we're going to bind to the AEAD algorithm set. And what algorithm are we going to do? We're going to do HMAC 256 using CBC AES. So the CBC AES is the actual crypto, the encryption, and then the HMAC 256 is the authentication piece, right? So this is, again, authenticated encryption that allows a user to know not only data was secure and not seen on the way out, but also they know who they're talking to, okay? We set the key of the algorithm, and we set the authentication size, how large the tag is, and then we pull out an accepted socket that allows us to actually do read and writes on it. This is a socket we're going to use to write data to the kernel to do the algorithm, okay? The way the AED is laid out, again, we have 4 padding bytes, which is going to be just 4 regular bytes. We have the additional authenticated data, so just 4 padding bytes, and we also have 4 payload bytes. Now we're going to send that payload, but again, before we do anything to actually trigger the decryption, we're going to run that splice operation. That splice operation is going to create a pipe that glues together the op socket where we're actually doing the operations on. It's going to glue that socket to the target file descriptor. So again, that file descriptor will be appended to the scatter list in the input scatter list for that socket. What this allows us to do is arbitrarily write 4 bytes to that file descriptor, which, oh, by the way, the target here is user bin su. And then when we go at the bottom here and we os.system on user bin su, the actual version of user bin su is not even changed on disk. We have a local page cache copy in the memory of our program that we can run that is just shellcode or run as UID 0. And as promised, guys, I'm going to run the exploit here live on my virtual machine. I don't have the most recent up-to-date kernel, but still March 27th, it proves the point. I'm going to run the command that copy.fail published. All they do is they take the exploit, you curl it out, you pump that into Python 3, and then in the same bash line, run su, and then bada bing, bada boom, I am root without typing any passwords. Now, if you're concerned that your org is affected by this, or you want to make sure that there's a way that you can like disable those crypto algorithms, first of all, there is a new mainline commit, A664B, which reverts the 2017 optimization that makes the input scatter list and the output scatter list the same to do the in-place optimization. And then also, if the algorithm module, the AEAD module is compiled as a separate loadable kernel module, then you can use this script here to remove the module and make sure it does not load on boot by default. That being said, if you don't have it loadable separately, obviously you have to use a version of the kernel that does not have it, either through local recompilation or a new version of the kernel that maintains this commit. Anyway, guys, that's it for now. Thanks for watching. I appreciate it. Sorry that was super deep and technical, but that's just the nature of the bug sometimes. If you like this video, hit that sub button. Check out this other video. I think you'll like just as much. I'll see you over there. Take care. Goodbye.